All right, we're back. We are on page 1 of notes 5 of Calc C, and we are talking about series, right? Infinite series. Do they converge? Do they diverge? How can we tell? And we've met some really famous series, the geometric series and telescoping series. And now we're going to talk about some different types of series. We also know the nth term test for divergence. So that can never tell you if something converges, but it could tell you that it definitely diverges. And that just says if the limit of the nth term is not 0, then the series definitely diverges. If the limit is 0, you don't know anything. All right, so let's talk about this next thing we're going to do. It's called the integral test, and it's related to another type of very famous, really easy to work with series called p-series. So let's see what it all comes down to, right? So hopefully you remember Riemann sums, because this one is sort of based on the concept of a Riemann sum with like a base of 1. So if a function is decreasing, so we're looking here, if a function is decreasing, what's true about a right Riemann sum? And I drew a figure that can help you out. So if we look at this, our right Riemann sum, so like 0 to 1, our right Riemann sum is inside, and then here are right Riemann sums, inside, inside, inside. As long as the function is decreasing, we're always just kind of like nestled inside of our integral. And so since that's the case, if the integral converges, but remember you're going to infinity, so it's going to be an improper integral, but if the improper integral converges, then the series also must converge. Now, one caveat to that is that your series would need to be positive termed to kind of like trap it between 0 and the function. But as long as that's the case, we can say that if the integral converges, the series converges. We can also say if the integral does not converge, that the series diverges. So the idea is that we're treating each of these, so like this is a1, this is a2, a3, and so on. And we're going to add all those up, see if we get a sum. If the integral converges, we must get a sum. And that is basically the integral test. So the integral test is our 4th series test. So we have geometric, nth term, and telescoping, and now we're on the integral test. Eventually I won't be able to name them all, but well, maybe if I just keep going, I will be able to, I don't know. So there are a couple of requirements. So given that a sub n is equal to f of n, that like happens a lot, right? When we're doing the nth term test and we had to use L'Hopital's rule, we kind of like worked with that for some f of x, and f of x needs 3 things to be true. It's going to be positive, I'm going to do it in different colors, continuous, and decreasing after some point. So it doesn't need to be decreasing initially, like eventually, because you can always add up a finite number of terms. Then it's the question, like from that number on, will it converge, will it diverge? So basically what this says is that if f of x is positive, continuous, decreasing after some point, then the series does the same thing as the integral. So either your series will converge if your integral converges, and your series will diverge if the integral diverges. So it all just comes down to, well, a lot. It doesn't just come down to anything. You have to show that well, usually you just state that the function is positive and continuous. Decreasing, you might need to find the first derivative, but often we can just make the argument that like the numerator is a constant, the denominator is increasing, so the function itself must be decreasing. I don't know, we'll deal with that. And then we have to actually do the integral, so that's fun. So let's see if we can do this. So you can use the integral test with a calculator way more often than you can do it by hand, because a calculator is more than capable of figuring out, are you positive, are you continuous, are you decreasing? It's just like a little bit easier. So let's see, I'm gonna like, just to do this problem, I'm gonna say that f of x is x squared over 2 to the x. And so therefore a sub n is f of n. So that's kind of like what we need to be able to do this. And then this is definitely a calculator problem. Can we do this by hand? I think you can do this with integration by, I want to say integration by parts will work on this, but I'm not actually sure. All right, so f of x is x squared over 2 to the x. I think of the integral test as like the ultimate test to use when you have a calculator available, because it can kind of just do the work for you. So for example, like we know eventually this is going to decrease because the limit is 0 because polynomial grows much more slowly than an exponential. So if I try to solve the derivative of f of x with respect to x is equal to 0 for x, let's see what we get. All right, so this or this. All right, so what about if, so that's not what I wanted. I just want to check derivative f of x with respect to x such that x equals 3, right? So I need this to be negative, which will tell me that the function is decreasing. And it is, it's barely negative, but it is negative. So we have a function that is decreasing. It's definitely a positive term because it's, you know, a positive divided by a positive. And it's definitely continuous because the only place this would equal, well, the denominator never equals 0. So definitely continuous. So I just need to figure out the integral. So I'm going to do the integral from 1 to infinity, but like technically you should really go 3 to infinity and then just add the first term and the second term. But if it converges from 1 to infinity, it converges from 3 to infinity. So let's do that. 1 to infinity. Well, we get a value, and that's all that really matters. Turns out it gives you the exact value. Oh yeah, I was going to look at that. Integral of f of x with respect to x. Does this look like it kind of looks like integration by parts. Oh yeah, you would just, I would do the table method on this. I would let u equal x squared, I think. And then make it x squared times 2 to the negative x, I think, and go from there. And it's gonna like terminate eventually because the derivatives of x squared go to 0. Anyway, I'm gonna go back to the notes and fill this in. So let's see. So what I like to see, and you don't usually have to prove this for me, and like AP exam type stuff, usually they would ask you to like find the intervals on which this function is decreasing or whatever. So I'm going to say f of x is positive, continuous, and decreasing for x greater than or equal to 3. I'm going to say that the integral from 3 to infinity of f of x dx converges. Now, how do I know that? I know that because the integral from 1 to infinity converges. So from 3 to infinity will also converge. Therefore, the sum. So I'm going back and forth on these numbers, right? So decreasing from 3 to infinity, and that's what I needed. So I did the integral from 3 to infinity, which I really didn't do. I went from 1 to infinity. But knowing that the integral from 3 to infinity, that doesn't look like an infinity. From 3 to infinity converges tells me that the sum from 1 to infinity converges because 3 to infinity is converging. So just add the first term and add the second term and definitely converges. So n squared over 2 to the n converges by integral test. So this, I mean, it makes its way onto the free response every once in a while on the AP exam. So it's a good one to know. I mean, it doesn't come up, I would say it doesn't come up as often as all the other ones, although it's intimately related to a very famous type of series, the P series, which we'll get to in a second. So let's see, use your calculator again. So let's say let f of x be x. This looks like partial fraction. No, not even, because the denominator does not factor. Could we do this? Oh yeah, you do like a weird like complete the square u substitution thing. I think maybe you get like an arctan and a natural log potentially. Anyway, therefore f of n equals a sub n. Let's go to the calculator and we'll do the derivative and all that stuff. So all right, so f of x, let's define that, is x plus 2 over x squared plus 5x minus 3. And so is the derivative, I need the derivative to be negative after some point. So the derivative of f of x comma x, solve, answer less than 0 for x. So I'm doing this a slightly different way. This is interesting. So the derivative is just basically always negative. We're going from 5 to infinity for whatever reason. So from 5 to infinity, the derivative is definitely negative because it's negative everywhere except at those two values where I guess it doesn't exist. So that's good to know. And then we need to know if the integral converges. So integral f of x comma x. I'm going to go from 5 to infinity because that's what the summation does. And we get infinity, so diverges. All right, so we are allowed to apply the integral test. And that's important, right? We needed the function to be positive. I didn't check to see if it was positive. I'm pretty sure it's positive. Oh, I bet that's why we're starting at 5. I'm just going to assert that it's true. I'm going to say that f of x is positive, continuous, and decreasing for, I guess, for x greater than or equal to 5. The integral from 5 to infinity of f of x dx diverges, which therefore, or that implies that the sum from 5 to infinity of a sub, you could just say a sub n, or you could say f of n. I'm going to write it down though, as n plus 2 over n squared plus 5n minus 3 diverges. I'm going to say as well, because it makes a better sentence, by integral test. All right, and that's what you need to do. So the calculator is a big help because of the derivatives and the definite integrals. But you know how to do most of those things by hand. It just depends on, you know how to do all those things by hand. It depends on the integrand. Like, can you deal with it? Who knows? But that's the basic idea. All right, so I will be back in the next video to do more of these. I think we're doing them by hand because it says at the bottom of the page there, do these by hand. So we'll see how that goes. Anyway, see you in the next one.